So to start with, as I was introducing, I would like to give an, let's say, a comprehensive overlook to Shor's algorithm and Grover's algorithm. The first one, uh, just a quick review, is devoted to factorization. Okay, when you have this integer number and you want to find the prime numbers that compose this integer number, this is a super hard problem, okay, to solve with classical devices because of the way a classical computer works. Okay, if you would be interested in solving this problem, you will have to go for an exponential number of bits, okay, increasing with the value of the integer number you want to solve. Okay, and that's a lot. That was one of the first applications of quantum computer. Shor came up with this algorithm capable of doing that in a polynomial time. Okay, this is Shor, and the algorithm relies. This is just a quick review of it. Relies on quantum Fourier transform, which is the thing that I was commenting previously. And yeah, the fact that complex algorithms are supported by modules made out of simpler algorithms is also a remarkable fact to comprehend the level of complexity of our quantum circuit. Okay, because already quantum Fourier transform is a module implementing a lot of correlations in our system, okay, impeding us to simulate such a system with classical devices. Okay, and that's one of the main limitations for it to be implementable in current systems. Okay, but as you can see, in case of achieving fault-tolerant quantum circuits going for a super high number of qubits, okay, we could be able to beat classical standards, solving this factorization problem. Okay, you see that in case of quantum circuits, we would be able to scale our problems polynomically against the exponential increase in number of bits for the classical device. Okay, that's already a very, very important consequence or result from quantum computation. Here you can put some numbers on it, and you see that for the classical algorithm, okay, we would need 317 trillion years to factorize number with 617 digits, okay, against the 8 hours that would the Shor's algorithm take for solving the very same problem, okay. And that is something that can be achieved, okay. That is theory that can be achieved with the proper quantum devices. Okay, it is not something that cannot be done in reality. Okay, it is not something potentially useful. It is something that exists in theory, and we only need the quantum hardware allowing us to get to that point. Okay, that's super important to remark. Okay, since it is still far from our reach, this Shor's algorithm, there have been many attempts to cut the number of qubits needed to solve such a task. Here are some papers devoted to that goal. Okay, and I would like to highlight this one in particular because it's dealing with something that I work on currently. Okay, for my PhD and the things we do in Multiverse, which is trying to scale these complex algorithms, okay, based on things such as quantum Fourier transforms, quantum amplitude amplifications, quantum phase estimations that are really difficult to be implemented, okay, trying to translate that into variational quantum circuit, okay, which is something that I'll be explaining later, but it's really the way to achieve a certain goal, okay, without having to perform such complex and still far from reach algorithms. Okay, those are based on a hybrid approach using classical and quantum devices, but they are something that can already be achieved with the actual quantum hardware that we have today. Okay, so this is the other example I was talking about. This is Grover's algorithm. Okay, again, just a quick review. This problem is oriented to solve the task where you have an unstructured database of an element, okay, and you want to find a particular entry, a particular element inside your array, okay, when you don't have any pattern related to your data set, okay, and you don't have any further information allowing you to, let's say, cut your search space or find some shortcut through it, okay? You know that in classical terms, you should go for n calls to the database, in the sense that you have to check if every single element in your data list is the one you're looking for, okay? The average could be n/2 because you can find that the correct one is the first entry, but you could also go for the last of it, and the average is n/2, okay? So Grover proved that this number could be reduced to n to the power of 1/2, okay, which is already a beautiful increment, and yeah, let's say speed up coming from quantum advantage, okay, as well as shorts. So this is some attempt to implement such an algorithm in actual quantum hardware. Still far from giving quantum supremacy or quantum advantage, but we are on track, and it proves that, in fact, quantum algorithms are useful for solving tasks that cannot be tackled by means of classical solvers.